So I've got my textbook, lots of notes there. You should have the same. Got my calculator stuck in there so you can see that there's a bit of a hill here. And if I take my ear pods and I set it on the hill, it doesn't slide. Well, obviously, there's got to be some friction in here. But when I tilt it up a little bit, then it slides off. How does the angle that it's tilted affect the coefficient of friction? Or does it at all? Let's see if we can draw a free body diagram to show this. I want to begin by drawing our free body diagram and figuring out what kind of forces are acting on the object. As always, the mass is pulled straight downward due to the gravity of Earth. We call that our force of gravity. Remember that we have a normal force, and this is a little different than what we've had before. Because remember, the normal force is perpendicular to the surface. So it is pushing from the surface upward on the object. We have some kind of force pulling it down the hill. And this is related to our gravity. And I'm going to call that our FA. It's our applied force. It's the force that's causing it to move. We're going to talk a little bit more about that. We also have a force of friction. And remember, friction always is in the opposite direction that the object is moving or trying to move. So we think we're pretty well done, but there's two other things we're going to involve in this triangle or in this diagram. First of all, if the normal force is upward there, we have an equal force downward right here. And we call this the perpendicular force. This perpendicular force is perpendicular to the surface, so there's a right angle here. It is equal, the perpendicular is equal to the normal force, just opposite directions. The other thing we have is we have what's called a parallel force. And if we make this right angle triangle here, we can see that this force here, this force parallel, so let me write those things out. This is perpendicular. And this is parallel. This force here, this parallel, is parallel to the surface. And it is also parallel to the FA, the applied force. So what we see is that our FA is equivalent in this example to our F parallel. Now what I see is I see this triangle here, and I'm going to redraw it for us. So I've got this triangle with this downward force of gravity, this perpendicular force here, and then we have at a right angle to our perpendicular force is our parallel force. The only thing missing is the angle, and that's the secret to this whole problem. This angle here is the same as this angle of the ramp. And once we have that, we now have our complete free body diagram, and we can solve many, many different equations. So we have a box with a mass of 1,500 grams sitting on a slope of 30 degrees, and I want to know the coefficient of static friction. So what we're making a little assumption here is that if I increase that slope at all, the box is going to start to move. So we're right at that tipping point between when the box will move and it won't move. Anytime you have a problem that you're given the mass, I think we should right away always find our force of gravity. And in this case, we have 14 5.715 newtons. Let's remember that this is an angle of 30 degrees. And we're going to get all of our other forces drawn in here. I have a force of friction, which is opposing the object moving. And we also have a normal force. That's the ramp pushing this thing upward. Remember that that is equal, opposite in direction to this force, which I'm calling a perpendicular force. And then what we also have is we have this downward force going down the hill. I'm calling that an applied force. And it is equal to this force here, which I'm calling an F parallel. Once again, I find it much easier if I redraw this triangle just a little cleaner, separate from my free body diagram. So once again, I have this force of gravity. I'll put this over here of 14.715 newtons. I have a force going this way, and I have a force going this way. This I'm calling perpendicular. This I'm calling parallel. And that's perpendicular and parallel to the surface of the ramp. And we know that this is the 30-degree angle. I'm going to label my triangle using the trigonometric ratio name. So this is my hypotenuse. This is my adjacent side. And this is my opposite side. We know that the sine of our angle is equal to the opposite divided by the hypotenuse. With a little bit of algebra, we would know that our opposite side is equal to the hypotenuse multiplied by the sine of theta. So in this particular example, we know that we would have 14.715 newtons times the sine of 30 degrees. What we're going to end up with here is a opposite side, which is equivalent to our parallel side. And the answer here is 7.3575 newtons. Okay, so once again, remember, this is our parallel. That's the opposite side. I can do the exact same thing with our cosine of theta. That equals the adjacent over the hypotenuse. And that'll tell us that our adjacent side is the hypotenuse times the cosine of our angle. Once again, that's 14.715 newtons times the cosine of 30 degrees. And that's going to give us a value of 12.744 newtons. That's the adjacent side. Remember, this is our perpendicular. Okay? Now, I want to remember that this perpendicular side here is equivalent to our normal force. So this, our normal force, is 12.744 newtons. Our force of friction, we didn't have it, but what we did is we found that we had our FA. Our FA here was 7.35, and that's equivalent, sorry, our parallel was 7.35, which is equivalent to this, that force right there. So this is 7.3575. Because this object is not moving, it's not accelerating, according to Newton's first law, it needs something to make it move. This force equals our force of friction. So our force of friction here is 7.3575. And now we have our frictional force and our normal force, and that's going to lead us to the coefficient of friction. So our coefficient of friction is our FF divided by our Fn. So mu in this example will be 7.3575 newtons divided by 12.744 newtons, where mu has a value of 0.577.